Hello, my name is Frank McKenna. I'm here at UC Berkeley working for the Neary Sim Center. In this video, we're going to talk about structs, data structures, and abstractions in C. So what do we mean by abstraction? Abstracting data is the idea to reduce the complexity by removing unnecessary information, i.e. we want to think bigger and ignore the minutiae, the minor details. And we've already done that in the C. Remember the computer, zeros and ones, but we're already thinking in terms of manipulating floats, integers, doubles, and strings. So C is already giving us a layer of abstraction. What C also provides, though, it allows us to create our own abstractions. So how do we do this? C structures, powerful features. It allows us to put together our own abstractions. It is a struct that we're going to use. A struct is a composite data type that we define that allows us to physically group a list of variables under one name in a block of memory. So here is how we define a struct. The struct name is the name we're going to use. The keyword is struct. And then inside the curly braces, we put as many different types of variables as we want, including structs. And that allows us to group together in one block of memory a certain data type. For example, we saw where for example, a float had 4 bytes. When we group together a struct, it has as many bytes as variable types in the thing. It actually sometimes has a few more, just to bit padding. So here, let me quickly demonstrate an example of a struct. So in this case, we're going to declare struct point. So point is going to be a type of struct, and it's going to have 2 variables inside it. It's going to have an x coordinate and a y coordinate. Note the semicolon here at the end of the curly brace. So now we're going to have a function main that uses a struct. So to initialize P1 and P2, which are 2 point structs, we use this syntax right here, struct point P1, struct point P2. If we want to initialize the data, as we have done previously in arrays, we put things in a comma-separated list inside our curly braces. If, on the other hand, we can do the initialization again outside by just using this point, P2 point X, P2 point Y refers to the X and Y variables inside the structure. And then finally we can do a printf of the 2 points, again P1.x, P1.y. Now I find this rather ugly, and an awful lot of other programmers do as well, which is why they make use of something in C called the typedef. Basically a typedef is a way to create a new type name, and it doesn't really create a new type, it just creates an alias to an existing type. So if you wanted to do, say you didn't like the term float and you just wanted to replace float with numtype in your program, where numtype was really a float, you'd define typedef float numtype, and then you could use numtype inside your program. Well, I told you I did not like having to do this for a struct, so we can use typedef again now for our structure point. So it's typedef structure point, and then at the end we put in what the new alias we'd like. In this case I'm using large P point. And then now inside the program I can create P1 of type point and P2 of type point and get exactly the similar look that I really like. And everything else is pretty much the same within the program. So typedef is just a way, creates an alias for us that greatly enhances the look of our program. So what are data structures? In computer science, a data structure is a data organization, management, and storage format that allows efficient access and modification to the data. That's a quote from Wikipedia. What it really does is allow us as programmers to find efficient ways to manage and store our data objects. Like where do we keep our points? How do we access the points? What's the most efficient way to access the point given the way given what we want to do with points? So what data structure we use really depends on how the user wants to access the data. And while C doesn't actually provide any built-in data structures, it does allow us to create our own. All the common data structures, for example, arrays, stacks, queues, linked lists, trees, and you can come up with many of your own data structures that might be more efficient for your particular use. You can actually do that in C. And I'm going to provide an example now of a linked list data structure. Before I do it, let's just show you what we're going to create. We're going to create a header pointer. This is going to be a pointer, which is going to point to a point. And in each point we're going to add a pointer type. That pointer is also going to point to a point. So each point is now going to have a pointer to a point. And when we add these points to our linked list, we're going to set up the pointer structure so that if we start at the head, we can go through every single point in our linked list until eventually we come to a point that has a pointer that points to 0. So we're going to stop because we realize, hey, we've reached the end of our list. So let's demonstrate now. I've got 2 code segments coming up. In the first segment, we're just going to create structure. We're going to have our head node, and then we're going to add to it a whole bunch of points. And in the second file, we're then going to go search through this points linked list for a certain point. So here's the first part of this linked list.c file. Again, we're just setting up this linked list data structure. So again, I'm using the typedef struct point. I've got my big point at the end, so I've got my typedef point. Inside point, I'm giving it a tag now. We're going to have, each point is going to have a tag, an x and y location, and then this structure pointer next. So next is a pointer to a point. You note here I have to use kind of the old syntax. I can't use the point syntax. It hasn't actually been declared yet, so I'm using the old syntax. So here's my head. I'm defining my head. The points, initially this pointer is going to point to nothing because I have no points in my program. So what I'm going to do to get the points into the program, I'm going to open up a file. This file is coming from argv. So argv1 basically will be the name of a file containing a whole bunch of points. They are in a certain format. We have an integer, comma separated list, integer, float, float. So this while loop here will read every line in the file, and for each line in the file it's going to create a point. So I'm going to malloc a point, malloc size of point. Okay, before we've been mallocing integers and floats. Now we have this new type, so we can use malloc on it. We just give it the size of point. The program knows how big a point is. We're going to cast again from a void pointer to a point pointer. And that's the sort of the regular syntax we saw when we were doing memory allocation. For each point we're going to set, we've got a new point now, we can set the tag x and y in the point. Notice here I've got the arrow. This is how we've got point. The next point is a pointer. So instead of using a dot, we have to access the tag x and y inside a point with the arrow sign. And then finally, after we've put everything in it, we're just going to set that the new point we've created, we're going to set it equal to whatever points is, and then we're going to set the points to point to our new point. And that way we add every single object into the linked list. If you want to figure out just exactly, if we've got a file containing four points and we add them to this list, it might be beneficial to see where exactly the points to when this little while loop is completed. And again, we're using a while loop because we do not know how many points are in the file. So that's why we're not using a for loop. Again, a while loop because we don't know how many points in the file. And we end the while loop when we reach the end of file. So next, let's search for something in this list. So basically what this program is going to do, it's when you run it, you're going to enter the points file, and then it's going to pop up something on the thing, enter a point to find. It's going to read in that point, and then it is going to search for the point. So how do we search for the point? Well, we set another pointer. We're going to create another pointer, current point. It's a pointer to a point. This and points are going to have, in memory, they'll be pointing to the same object. And then basically we're just going to go down through this list looking to see if if the point is not equal to 0, is the current point's tag equal to the one we're looking to find? And if it's not equal to the one and it's not 0, then we just want to go down to the next one in the list. So that's what this is doing. So again, we start here, we keep going down the list, we look at the tag. If it's not their current one and the pointer is not equal to 0, we just go to the next one in the list. And then when we're done, the current point, it's either going to point to something or it's going to be equal to 0. If it's equal to 0, we haven't found our point. But if it's not equal to 0, we found the point. So that's how we do points in a linked list, searching for points when we put them into a linked list. If the access pattern you have to a large collection of objects is similar to searching randomly for a point, we would never, ever, ever use a linked list. This is just an example to show you how easy it is to create such a data type in C. So structures, pointers, and data structures, they're allowing us to think in terms of looking at points in a file. So we've got this idea of abstractions. So we're all civil engineers. So let's think about abstractions for a finite element application. Say you're tasked with coming up with a finite element application that you've decided you're going to write in C. What are the abstractions you're going to need? You know, we saw points, so let's come up with abstractions for a finite element application. I would put it to you, we'd have some nodes, elements, constraints. We're going to have some idea of vectors, matrices, loads. We're going to need somewhere to store all our nodes and elements and loads, so we'll just call that a domain. And then also we'll have something to do the analysis. So these are the abstractions. Now how do we code these up? So let's look at the simplest of these, the node. What is a node going to have? Well, it's going to have a tag. It's something tag so we can identify it, so we can go figure it out. Each element is going to have some nodes associated, so we need to be able to go find our node among a list of nodes. So the node itself, the element's going to need to figure out its length, so the node's going to need to have some coordinates. The element's going to need to determine the state of strain in the element, so for that the node's going to have to provide the displacements. And then we said, do we also put in the velocities and accelerations? Are we interested in them? We don't need them if we're doing a static analysis. In a transient analysis, we don't need the velocities and accelerations if the elements don't need them, but we might want to look at the results later if somebody was, to say, interested in the floor accelerations. So these may or may not want to go into our application. So basically what I'm trying to point out is, what goes in here really depends on what the program's going to do. So it takes an awful lot of thinking beforehand. You've got to spend some time thinking just exactly as what this application is going to do. Is this going to be a one-off application that I'm going to write for my dissertation, or is this going to be something that I'm going to use for years and years to come, and which other people are going to want to spend some time at? So do I want to put as many different features in here as I think might be useful that allow me to extend it later. So let's assume that we've decided that we've got a two-dimensional problem and we're going to store 3 displacements. So how would we do it? We could do it this way here. Define our structure node. We've got x coordinate and y coordinate, and then the 3 displacements. Alternatively, we could store it like this. We could have an integer tag and then store our coordinates and displacements inside an array, a fixed length array. So which we choose? I'd put it to you that the element might find it easier to use this approach. For example, it could do some loops, for loops, loop over things, whereas in this approach it would have to do a dot for everything. So I would go with this approach, but again, it's up to you. So now let's look at our program that actually uses nodes. So we have a typedef node. We have these functions, node print, node setup, which are defined later further down in the file. And then the first thing we do is we create 2 nodes. We set up the nodes. This is just going to set the coordinates. So node setup, we have to provide the node whose coordinates we're going to play with. Node print, again, we're just providing the node, so we're passing the address of the node into the function so that the function can go play with the node. And inside the function, the node is going to set the tag, the coordinates, and the thing. And because these are pointers coming in, we're going to use that arrow to set the value. We've seen the arrow before. Again, because these are pointers, when we access any of these things that are defined in the structure, we have to use the arrow. So that's one example of using, say, a node in a main program. We, of course, though, are interested in setting this up for a large finite element project. So we want to think even bigger abstractions, bigger utility functions. So basically, we're going to come up with the idea of a concept of a domain. We're going to set the nodes in the domain, the number of nodes, and the max nodes equal to 0. And then basically we're going to have some function defined somewhere, probably in domain1.h, that is just going to add a node to the domain. So then the question with the domain is, how do we store all the nodes? So this is bringing us back to the idea of the data structures. I mentioned previously in C we can do array, linked list, doubly linked list, trees. There's hybrid approaches. And again, as I mentioned, it really depends on what the access pattern is. So when we write the elements are going to be the things looking for the nodes. How are the elements, how do you think the elements are going to access the nodes? And that'll really come up with how you think the best way is, which data structure is best for to store the nodes. The data structure to store the nodes might be something different to store the elements and the loads as well. So this is an example of an array data structure for storing the nodes. We did a linked list for the points. So this is an array. So an array, we have a header that's pointing basically to an array. Each element of this array will point to a node object. And in this file, I have how that is implemented. Let's say I didn't like the nodes, say I wanted a linked list. We've seen a linked list before. So I'm going to have some nodes. Each node is going to have a pointer. And I'm going to be able to put something into the list and take something out. So we saw how to do that with points. And here again, we searched through the linked list, and here is how we search through the array. They're both order n searches. So in the past few slides, we've looked at nodes. Nodes are a very simple structure type to create. We also looked at the domain. They were the data structures. They're holding the containers so that the other nodes, elements, and other objects that are going to exist in our file element application can access the nodes and other things. So now what about elements? Elements are a little bit more complicated in the sense that we have now both data and functions associated with an object. We have functions associated with the object because we want to use elements of different type in our program. To do that, we're going to have to use something called function pointers. I'm type defing here. I'm using type def again here to define a function pointer for myself. We're going to call it element state function, and it's going to take a domain. It's going to return, say, k and p. It's going to probably take in some other stuff. When we construct an element, we're going to assign whatever function goes into that element depending on the element type. So it starts to get a little bit more complicated. Function pointers are a little bit fun to play with, but it is possible. It just gets a little bit more tricky. I have created a finite element application in C, and I've created another one in C++, which is an object-oriented extension to C. I found that the C program, while it was more difficult to write, it ran faster. I was getting about a 10% improvement in performance over the C++ program. Ultimately, I released the C++ code just because it was a lot easier for other developers to add their code into a C++ program than it was the C.